So yesterday, the last thing we saw, what we saw mostly was the definition of cluster varieties as this union of algebraic tori that we glue along the mutation map or transition functions induced by mutation maps. And then we made this observation that actually the transition functions do not include any signs, like no minus signs. We don't actually need subtraction in order for these functions to be well defined. And that led us to the definition of tropicalization, or more generally, we can work over semifields. So I want to recall the tropical cluster variety and its definition, and then tell you how we can deduce the definition of the cluster complex that encodes the combinatorics of all the seeds and how they are related from this point of view. And then we'll move on to then we're going to, by the end of the class, we're going to just look at some results that we can have for finite type cluster algebras and how this kind of abstract schemy notion of tropicalization, of Mark-Goncharov, is related to a more algebraic, more simple approach to tropicalization of ideals using Gröbner theory. So let's start recalling the tropicalization. So we've seen yesterday the definition of the seed tori. That was just C star to the n plus m with a distinguished set of coordinates given by the coordinates of the cluster of my seed. And then we saw that we can define, we're going to take this as definition, the integer tropical points, so the seed torus, but now working over the tropical semifield. So ZT was, as a set, the integers with the operations maximum for addition and usual sum for multiplication. So this tropical integer points of the torus are then defined as the co-character lattice of the torus, or identified tensored over Z with ZT. And here I'm considering just the multiplicative group of ZT. So ZT multiplicative group is a bit confusing, is the integers with addition, because this is my multiplication. Okay, so then we looked at the tropical transition functions. And this was just using the usual mutation rule, but now replacing, well, addition with taking the maximum and multiplication by taking the sum. So if I have a point A1 to AN plus M in a seed torus, well, it's tropical integer points for some seed S, and I have another seed S prime that is related to S by mutation in direction K, then I would send this point, which I can always think of now as a lattice point. I send this lattice point to the following. I keep all the entries that are not in the kth position, and in the kth position, I tropicalize the usual mutation formula, which amounts to taking minus AK, the kth value, and then adding the maximum of the sum of all AI, where there's an arrow from I to K in my quiver, and the sum over all AJ, where J is such there's an arrow from K to J in my quiver. And all the rest of the indices stay the same. So just to be clear here, so S is a seed. That means it is a quiver together with a tuple of cluster variables, and these are arrows in my quiver. Okay, so for the definition of the cluster variety, we had to be a bit careful because the usual version working over a field here was not well defined everywhere on the torus. We had to kind of be careful that actually we land again in a torus and we don't, create a zero entry in this position. But in this case, we don't have this problem, right? This is a piecewise linear map from one lattice to itself, and it is well defined everywhere. Okay, so now with this we can define the tropicalization or the control tropicalization of this cluster variety. So this AS was just the union of the tori itself, glued along these mutation maps. And its tropicalization, I will denote it like this. So S is a seed all the time. So this is now the union over, well, my tropical seed tori. So just several copies of the lattice, how you can think of it. One such copy for every seed S prime. That is mutation equivalent to S, so I can obtain it from some finite sequence of mutations. And I identify 2 points in 2 different copies of the lattice if they are mapped to each other under some composition of these piecewise linear maps. So I will write this just as I wrote it in the classical case, glued along the tropical transition functions. And as these maps are defined everywhere, really here, a point in this space, so a point in AS tropicalized, or this is also sometimes called the tropical integer points, using like the algebraic geometry language, is really a class of points so one point in every seed torus, in every copy of the lattice. And such that, okay, I'm running out of space. Such that if S and S prime are related by mutation. Okay, no, I need more space. I want to do this better. So before saying what a point is, let me just introduce notation. So if I have S and S prime, 2 seeds, such that there's a sequence of mutations relating the two, then I denote by mu S S prime, and yeah, I can do this tropically or not, the composition of the corresponding maps. So I start at S. And now I can write down more formally what is a point. So yeah, similarly for the tropicalizations. And then a point A in the tropical cluster variety is a tuple, or an infinite tuple, AS prime, so that S prime is mutation equivalent to S, and these maps send the 2 representatives to each other. Okay. Yeah. Any question?
So you're making all these identifications. So suppose I concentrate on one copy of one of these TS1 ZTs.
Mm-hmm.
Does it happen that 2 points in it get identified?
2 points in the same? So my definition here has one copy of this torus for every seed. So I don't have in my set of maps, I don't have any maps that go from the same seed to itself.
No, what I mean is because when you connect it to something else.
Yes.
And then something else comes back to some other point.
Yes. Yeah. And then okay. So okay, I think maybe what you're getting at is something that we would have to verify already in the original case, like that this is well defined, right? And or also the normal cluster variety over the complex numbers say that it is well defined. So what we have to verify is the co-cycle condition, that the two compositions of maps between the two same atli actually give us the same outcome, right? That we identify the same points. And that is true. So if you have two maps that go from, okay, it's a bit subtle, I guess, because so generally the seeds are associated to this infinite n-valent tree. So some tree where every vertex has valency n, but it is infinite. And we can associate a seed to every vertex by just identifying some vertex 0 where we place our initial seed, and then we walk away to all the other seeds. But of course, we've seen that these mutation patterns, they are periodic and sometimes. So although we have an infinite number of vertices, we will have only a finite collection of seeds that we actually want to consider. So we have to take a quotient to actually get down to this, or identifying vertices in the tree that would give us the same seeds. Okay. Any more questions? Okay, so then let me give you the definition of the cluster complex from this setting. And first, I want to denote by NS plus the positive orthant in the real vector space associated to my lattice NS. Then one fact. Well, okay, yes, I could do that. Just take the positive orthant, but right. So one fact is that every one of these mutation sequences, if I apply it to the positive orthant in the lattice I have sitting at this seed, then it will still be a cone after applying all of these maps. So that means these piecewise linear functions, they always have like a hyperplane running through the space, and this is where they break linearity. But the positive orthant under such sequences of mutations always lies on one or the other side where the map is actually linear. So if I take the pullback, of NS prime plus or NS plus under the maps is a cone. And this is then in NS prime tensor with the wheels. And now I can define the cluster complex as the union of all of these cones. So there's one more thing to check, that the pullbacks of all these positive orthons actually, if I pull them all to the same copy of the lattice, or the real vector space associated, that they actually form a fan. But they do, and the associated fan is called the cluster complex. So for a given seed. We define. So yeah, so one maybe again this would be the proposition definition, and the proposition part is to check that they actually form a fan. And we're going to do an exercise in a second. Right. So the positive, the positive orthon would be all of these are non-negative, and then here I land inside the positive orthon if all of these are still non-negative. But now I do the other way around. I take the positive orthon here, and I consider its pre-image, and then I do get negative entries because I have a sign. Exactly. Yes. Yeah. Yeah. And depending on what's the map I'm considering and what's the S prime I'm considering, I get a different set of indices that satisfy that, and that would be one cone here. Okay, so define, and this is called the, yeah. Yes, it's the real cone. Yeah. This is maybe a bit of laziness. I could still just take integer points inside, but yeah, I just changed to the real vector spaces. And this is called the Fock-Goncharov cluster complex. And one thing that Gross-Hecking, Kiel, and Kontsevich show is that this is indeed like a fan realization of the cluster complex that I have associated with cluster algebra. So the cluster complex is a simplicial complex where the vertices correspond to seeds, and I have edges between two vertices if there's a mutation relation between them. And this gives us the same combinatorial object just as a realization, a realization of as a simplicial fan. Okay, so let's do an example. So if I start with a finite type cluster algebra, then this is true. So okay, maybe something. So this fan is complete if and only if the cluster algebra is a finite type. Otherwise, there will be gaps in my fan. And the very first example where I can see a gap is the Kronecker quiver, where my cluster complex looks like this. I have, I think for every rational value here, I get a ray, and these rays go closer and closer, but I am missing, if I have color, I am missing exactly the ray spent by 1 minus 1. And then, yeah, I think if you go up in rank 2, for example, to a G2 type cluster algebra, this gap becomes bigger. And yeah, so this is kind of, yes, yeah. So everything is part of my fan except the red ray. So yeah, so I think we're on the wrong side of the. So we're actually this picture is inside. Yeah, I think it's just the same. It's several copies of this lattice, and we identify by different by the maps. So the nice thing is working with the tropical cluster varieties that you can as soon as you fix coordinates, it's just a lattice. So that's why they are relatively simple. Just if you want to have some other statements, you have to be careful because you identify and you have these piecewise linear maps. Yeah, because you always have to go through sequences of piecewise linear maps. Yeah. Okay.
Can I ask a quick question? One observation is that about this Kronecker case, although the fan is not complete, it's dense.
Yes, exactly.
Is there any conceptual description or explanation of those cases for which the fan is dense, although it's not complete?
Oh, actually, I don't know, but this is also the only example I think I know, like spontaneously, where it is dense. So if you take the closure, you get the whole
That's right.
space, right?
I see.
Yeah.
Thank you.
Okay. Let's do an example. And as an example, I'm going to follow the example we had before of the affine cone inside of the Grassmannian 2-4. So we already saw the cluster variety as having 2 seeds. They're 5-dimensional complex tori with the Plücke coordinates indexed by the 2 triangulations we have of a quadrilateral. And the tropical transition function is this one. Right, so these are the frozen variables. This is the mutable variable. We're in type A1. So this is my map, and my cluster complex has the following 2 cones. Sigma S consists of all of those points where the maximum is achieved by the first term, and the other one of all the terms where the maximum is achieved at the second term. So I have my tuple of points. And so we're inside R to the 5. And these 2 are 2 cones that are half spaces, and they form a complete line. Okay. Right. So this is all I wanted to say on cluster varieties. I want to come back to the world of cluster algebras and yes, yes, yeah. Ah, yeah. So, okay, so maybe let's go through the computation. Um, mm, mm. Okay, so the question is, which points here give me a non-negative value here, right? And yeah, why did I get rid of x, y, 1, 3? Sorry. Yeah. So, yeah. Mm-hmm. Okay, yes. Okay, let me add this here. U13 is less or equal than the maximum. Yeah. Okay, I think I probably got a bit confused because I have so many frozen variables. And I want to allow my frozen, so I think the best way to now see this as a complete fan is when I take a quotient and just go to this one-dimensional space spanned by the first variable. Because in the end, yeah. So I think there's, so to generalize this definition of the positive ortho, like I don't really care about the values of the frozens. I can include here, I can actually split this into frozens and non-frozen and just have the positive orthant in the mutable variables. Yeah, because otherwise, I mean, in R5, I will not get a complete fan here. So, but yeah, modulo the frozen variables, this is the complete. So these are all frozens. Yeah, yeah, exactly. Yeah. Yeah, okay, sorry, this was maybe not a very illustrative example. I should have done one without frozen. Yeah. Okay. Right, okay, so I want to get back to finite type cluster algebras and to, okay, I don't know, maybe a bit of like story. I do appreciate a lot all of this work on cluster varieties, and I do appreciate a lot this paper of Grosshecking, Kiel, and Kontsevich and the work of von Kontrov. I don't know about you, but when I saw these definitions for the first time, I was very much confused and uneasy. And there's another theory of tropical geometry that is very, let's say, almost naive when you have an ideal. And it applies in the case of the Grassmannian and all other finite type cluster algebras. So what I really wanted to understand is if this notion of tropicalization has anything to do with the other one. So what I want to tell you now is that yes, it does. And in order to do so, I will give you a summary of how do we get more naively, more algebraically to a theory of tropical geometry, and how is it related to this one. And for that, yeah, let me do tropical geometry. Of ideals. And so the motivation here is the following. If A is a finite type cluster algebra, with cluster variables x1 to x capital N, so these are now all cluster variables of all seeds. Then I have an isomorphism of A with the quotient of a polynomial ring modulo some prime ideal. And actually, I is the saturation of the ideal generated by all exchange relations. And there is a theory of tropicalization of ideals, and a very naive question is the tropicalization of the ideal I related to the tropicalization of the cluster variety? And the answer is very nice. It is yes. And then, no, so this capital N here is different. Normally, I would have lowercase n for the number of vertices or the mutable vertices, but this capital N is some larger number. Or take all. Exactly. So it's all like running through all seeds. It's the generating set I use to define the cluster algebra. Yeah. Okay. Yeah, the saturation is radical. So I want to. Can I give you an easier definition of the ideal and then kind of postpone that saturation question? Or yeah. I mean, this ideal, if you don't want to think about too much in commutative algebra terms, it is the ideal that I get as the kernel of the map when going from the polynomial ring to the cluster. Yeah. So, and yeah, there's some more elements than in just the exchange relations. That's all. It's not necessary to get a presentation. No. Yeah, you don't. You know, this is like the. I'm simplifying a bit the context to make more nicer statements. Yeah, yeah. But if it's finitely generated, then you can get a presentation. The algebra has to be finitely generated. Yes. And this statement is still true if this is a generating set, a set of cluster variables that generates A, as yeah, then this is still true. Then you get the ideal as the saturation or the kernel of the map. Okay, so I'm not assuming you're familiar with the tropicalization of ideals. So we're going to do that now. And then I'm going to tell you the two statements. And you can let me know afterwards which kind of tropicalization you prefer, the one of cluster varieties or the one of ideas. Obviously, I have my preference, but let's see what you think. So we're now working inside a polynomial ring. So we have some polynomial ring k of x1 to xn. And I'm going to give you some definitions that we need to set up the definition of a tropicalization. So one thing that I can do if I have a polynomial here, well, I write it as a sum of its monomials. So this x to the m is now x1 to the m1, all the way until this x capital N to the mn. And m1 to mn are non-negative integers. And then I can pick a weight vector that is just some real vector with entries, some n vector with entries in R, and define the initial form of f with respect to w as a sum of monomials that occur in f, but I'm going to drop out some monomials, and this vector is going to dictate which monomials I drop. So f is going to be the sum over still all lattice points, but now I only pick those such that if I take the dot product with w, what I will get is the maximum of all the possible values that I get for taking dot product with w. So maybe let's call this n or p. I have so many m and m's everywhere. So that p dot w is the maximum over all m dot w, and I pick those m that have a non-zero coefficient here. Great. So great. If I do this to polynomials, I can easily extend this to ideals. Or should I? Maybe let's give an example first. Right. So if my polynomial is x cubed minus y squared, and I'm taking the initial form with respect to 1, 0, what do I get? X cubed, right? And if I do it with respect to 0, 1, I keep y squared, right? So that's the idea. Minus, yes. Thank you. I keep the coefficients. So if I have an idea, I also want to define the initial form of the initial idea. Of I with respect to w. Sorry, I forgot my notation. So in w of I is the idea generated by all initial forms of all elements of the idea. So and it's important here to consider all elements, because if I have one specific generating set of the idea, then its initial forms might not generate this idea. This leads to the notion of Bruckner bases, and there's a whole theory how to check what's the generating set here. Of course, this is inside a polynomial ring, so it is finitely generated, but it might not be generated by initial forms of whatever generating set you choose for the idea. Okay, so now with this notion, I can define the Gröbner fan. And that is a fan inside R to the capital N, where I choose my weights. And I will identify two weights if they give me the same initial ideal. So in my small example here, is there a question? Yes. Usual Gröbner spaces, just that I'm working with weights instead of monomial orders. Yeah. Not every weight. Yeah. Yeah, so generic weights give me, so generically I will always end up with one monomial when doing this, and then I can have a monomial order. But there are non-generic weights that will not give me monomials, and actually those are the ones we will be interested in for the tropicalization. Right. Exactly, those will be intersections of these cones. Yeah. So this is a fan that is full dimensional in R to the capital N. And maximal cones correspond to monomial initial ideals. So where all these, where the ideal is generated, initial ideal is generated by only monomials. So in this case, what's my Gröbner fan? It's a very weak example. We already saw, no, that 1, 0 gives me x cubed, and 0, 1 gives me minus y squared. And then I can move these weights a bit. And yeah, so at 2, 3, the ideal is homogeneous. It stays the same. So this is where the two cones intersect. And this would be my Gröbner fan. There's a bit of a subtlety that if my ideal is not homogeneous, I will only consider this inside the positive forcent. So the Gröbner fan of I is, I will put here greater or equal to 0. And this is like an extra condition I have to make if my ideal is not homogeneous. If the ideal is homogeneous, I can consider the whole space. But, yeah. So, right. Okay, so yeah, so I already commented that generically I will get monomials as initial forms, and the maximal cones in this fan correspond to these monomial initial ideals. But for us, it's actually very interesting to look at the initial ideals where the initial form is not monomial. And the reason is that for every weight vector here, let's put it non-negative now. There is a degeneration of the spectrum of the quotient of the polynomial ring by my ideal I to the spectrum of the quotient of the polynomial ring by my initial ideal. And if I take a generic weight, then I will end up with a hyperplane arrangement. But if I take non-generic weights, and if I take non-generic weights that give me initial ideals generated by binomials, and if these ideals are prime, then I get a toric degeneration. So that's a motivation to consider the following subfan. So the tropicalization of I is the subfan of the Gröbner fan of I consisting of cones or only those cones where the initial ideal does not contain any monomial. So this is a bit more than what we were hoping for to get binomial initial ideals. But binomial initial ideals will be the maximum, the maximal cones that we can get. So let's do an example. Yeah. In this case, as my ideal is generated by just one binomial, there is no initial form that I can take to still have this condition. Yeah. Right, so maybe one fact. The dimension of the tropicalization, let's call it T of I, is the Krull dimension of the quotient by I, of the polynomial ring, the quotient by I, or the dimension of the affine variety associated with I. Whereas here, the dimension is capital N, which would be the affine space where my affine variety lives. Okay, so let's do an example. And we're gonna stick with the Grassmannian 2-4. So we have our Plücker ideal generated by this relation. And whenever I'm in the case where my ideal is just generated by one polynomial, the maximal cones of the Gröbner fan are in bijection with the monomials. And this holds whenever the ideal is homogeneous. So here, every one of those corresponds to a maximal cone in the Gröbner fan. And if I have two maximal cones, one corresponding to this and one corresponding to this, well, then their intersection will correspond to the initial ideal generated by these two terms. So in this case, also for every monomial, I get one maximal cone in the tropicalization. And there are conditions on the weights that I will write down now that will exactly tell me when this happens, which cone corresponds to which. So then the tropicalization of I has three maximal cones. And I will index them by the monomial that will not survive. So T12, this monomial, it does not survive the initial form, taking the initial form. If I pick a weight in R to the 6, that satisfies that W12 plus W34 is strictly small or less or equal, let's take the closure of the cones, then W13 plus W24, and this is equal to the weight of the last term, W14 plus W23. Right, so if I take this monomial and my vector in R to the 6, I think about elements here also as being indexed by these two element subsets. So this is W12, 13, 14, 23, 24, 34. And then I take a dot product of this W with the exponent vector of my monomial. And in the first case, this is what I get. Right? P12 as exponent 1, P3 for exponent 1. So it reads of these two, and the other is this. Right, and then I have the other two cones, tau 1, 3. Yeah. And tau 1, 4, similar. Okay. Okay. So, no. So I want to give you one more definition of another subfan inside of the tropicalization that has to do with positivity. So as much as we have a notion of positivity on the varieties, we also have a notion of positivity in the tropicalization. And for that, I need the following. So if I have an ideal, and now I will work with real coefficients, then this is called totally positive. If it does not contain any non-zero polynomial in the subset here where I restrict to polynomials with non-negative coefficients. And the motivation for this definition is the following. That is, my ideal is totally positive if and only if there exists some weight vector. So ideally, the idea here is an ideal is totally positive if and only if the corresponding variety or its vanishing set intersects the positive orthant, right? Then I would say, okay, the variety has a positive part. This is a bit too strong to ask for. So what we have instead that is an ideal is totally positive if and only if there exists a weight vector. Just check my indices. Yeah. Such that the vanishing set of the initial ideal intersects the positive orthant. And so this definition on the level of the ideal is what guarantees this condition on the spaces. And then inside my tropical variety, if I am in the case where my ideal lives in the polynomial ring with real coefficients, then I can define the totally positive part of the tropicalization of I, and I will denote it by T plus, is the set of all weights such that the initial ideal is totally positive. Okay. Right. Okay, so this is all the preparation I need to tell you about the relationship between the two tropicalizations. Any questions? Tau of I is the tropicalization. Maybe I didn't write it. Yeah, tau of I or T of I is the tropicalization of I. So I have three fans here. Assuming that my ideal I itself has I can consider it in the real polynomial ring and it is totally positive. Then I can compute its Gröbner fan. Inside the Gröbner fan, I look at only those cones where the initial ideal does not contain monomials. And then I go one step further and I consider only those cones where the initial ideal is still totally positive. So we can look at this here. So if I'm in my cone tau 1, 2, we saw the initial form, well, these two weights win the race, so which means the initial ideal here is generated by this binomial. And in this case, the initial ideal is generated by the two monomials corresponding to these terms. So first of all, we can notice here that if my ideal contains a monomial, it violates this condition. Right? Any monomial, so an ideal containing the monomial, it doesn't matter what coefficient it has. I can change the coefficient and it will be non-zero element here. Right? So if I contains a monomial, I is not totally positive. So if I go here, first of all, if my ideal, so then in consequence, if my ideal is generated by a binomial, this means it already has to be totally positive. Because if I would generate, if I would take another initial form, I would be left with a monomial and I will not be totally positive. And so in this case, I'm already stuck. Because this is a non-zero element of this set, right? It's a polynomial with real positive coefficients. So in particular here, this tau 1, 3 is not in the positive part of the tropicalization of my ideal. And in fact, so I didn't write it down here, but the initial ideal with respect to this last cone, well, is generated by the one combination that we're missing, by these two terms. So in this example, we identify two cones that are totally positive. So the tau plus, tau plus is a full subfan. So if I have one element contained in tau plus, then all the elements in the same cone are also contained in tau plus, because they give me the same initial idea. Yes. Mm-hmm. Mm-hmm. Yes. Yes, yes, yes. Okay, sorry. Let me correct this. I consider in this case only weights, weights that are in the positive orthant but not zero. let's put here without the zero vector. Yeah. Because I mean, in this case, so your initial ideal would be just generated by 1, right? Ah. Okay. Yeah. Yeah. Mm-hmm. So the vanishing, this part is already empty. Okay. But, right. Right, but this is okay, right? It fits the definition, right? Because so the vanishing set is empty. So if I intersect with the positive orthant, it is still empty. And we also observe that this idea does contain a non-trivial element here. So it is not totally positive. Okay. This equivalence? Yeah, I mean, I can give a reference. I don't want to prove it now, but this is a lemma by Einsiedler, Dunkel. Okay, I think my timer thing is not working, and I'm going over time because I didn't have the bell. But let me stop here.
Questions? Everything is crystal clear. If there are no questions for this lecture for now, let's thank Lara again and